Thank you all for joining us for today's webinar. Before we begin, we'd like to go through a few housekeeping items. First of all of those that are joining us will be put on mute due to the large number of participants in today's presentation. If at any time you run into any technical difficulties, please email us at webinars@us.yokogawa.com. We will be having a question and answer session at the end of today's webinar. To participate in this session, please use the chat or the Q&A window in the lower right-hand corner of your screen. Also, please make sure that it is addressed to all panelists. We'll try our best to get to each of your questions. If by any chance we don't get to your question, we'll make sure to personally follow up with you and make sure that your question gets answered and taken care of. Today's webinar is being recorded, and at the conclusion of today's webinar, within the next couple of days, we'll make sure to get you a copy of today's recording, as well as the PowerPoint slides from today's presentation. Finally, as you exit today's webinar, we will have a short survey that we ask you to participate in. This survey helps us understand what you thought of today's presentation, what you thought of the topic, gives us ideas of ways in which we can improve and additional topics that we may be able to present on in the future. We'd love to hear your feedback. Later this year, October 3rd through 6th in Orlando, Florida, we'll be hosting our Yokogawa Users Conference. This is bound to be a great event filled with a lot of networking opportunities, A-list presenters, and a lot of fun, exciting events to participate in. For example, one thing we'll be doing is bringing attendees to a section inside of Universal Studios Island of Adventure and just have it reserved for that group of attendees. We'd invite all of you to attend. We'd love to see each of you there. With that, we'll jump into today's presentation, Key Areas for Consideration in Sample Handling Systems. Sample Handling Systems, Chance or Choice. Today's presenter is Trevor Hibdage. He's from the UK, actually, and we're excited to have him. Trevor has spent more than 40 years working on site, in offices, and in classrooms with almost every process analyzer that has been made, solving sample system design issues for a myriad of processes. Educated as a chemist and mathematician, he has worked with the oil and petrochemical companies around the globe to design safe, reliable, maintainable analyzer systems and provides a design and training consultancy to many end users and specialist suppliers. He has worked with Yokogawa since 1999 and has helped develop custom solutions to support a variety of internal needs. With that, we'll turn the time over to Trevor and thank him for presenting for us.
Hello, good afternoon, good evening. With an introduction like that as Analyzer People, you can guess correctly that I wrote it, but I have been working in analyzers for 40 years. I've seen every type of fault that you can possibly imagine and some that are unimaginable. And as an introduction, we are multinational here. I'm speaking to you from the UK. It doesn't matter where we are. The connectivity that we have these days is unbelievable compared to how we started the industry. More than 40 years ago, we didn't even have computers. So things have changed. One of the things that hasn't changed are sample system problems. So I've been asked to put together this presentation on sample systems. I've entitled it Chance or Choice. It's basically some key highlights about what goes wrong, why it goes wrong, what we can do to stop it. So what I will do is I'll launch straight in. We do have an opportunity for questions and answers at the end, but if you've got something that is so important that it can't wait to the end, flag it on the Q&A as urgent, and we'll see if we can't build it into the running of the system. So we're going to talk about some key areas for sample handling design. You've bothered connecting today because you have an interest in this. You may have specific problems in mind and you may need immediate help, but some of the areas that we consistently seem to be working with can be summed up in quite a few bullet points. So we're going to cover 5 areas, the classic pitfalls, what I'm going to start with, which is where do we do it wrong, and then move into how maybe we could do it better. Basic design strategies will be a few key points that will help us maybe understand why we've gone wrong, where we should work towards, which will highlight where in fact we should be focusing. One of the key areas that is going to come out of all this is understanding response times and what we can do about them and what are our expectations. As a wrap up, we'll go to future trends and try and throw some light on what's going on in development. So without any further delay, I will slip into classic pitfalls. I could carry on with anecdotes for several hours. One of the problems that we get is that perception of analyzer performance is one thing, actual analyzer performance is another. Please excuse me. I'm just going to skip through here and move on to reliability, perception or fact. Most analyzer problems are caused by inadequate sample system design. Perception or fact? How many times have we heard, oh, the analyzer's broke, go fix it, the analyzer's not working, the analyzer disagrees with the lab, that can't possibly be the reading, something's broken again. To be honest, it doesn't matter whether the perception is real or whether it is purely how someone else is looking at the system. If the analyzer system has a bad reputation, then it will not be used fully or maintained fully. So we can argue till the cows come home that, oh, no, that's not true, the analyzer's actually working. If it's a perception, we need to do something to change that perception. And unless we address this fundamental pitfall, we're not going to get anywhere with our acceptance of an analyzer system or our design. So response time is probably one of the most misunderstood and argued about factors in analyzer performance. And I'll make a statement here that an analyzer system that responds so slowly as to be boring or irritating to those using it or maintaining it will receive little attention and poor maintenance. A lot of people can sympathize or empathize with that statement, and it's something that we hear today in 2016. But if you look at the publication date from this particular statement, this was September 1959 in the American Chemical Society publication. So we're looking at something that is 50 something years old, and it hasn't changed. With the exception of model-based control where precision outweighs speed, it's still true. Analyzers that respond slowly that are irritating and boring, we don't maintain them. We don't look after them, and they fall into even more disuse or upset the perception of other equipment. So I want to summarize our classic pitfalls on this slide. Our primary consideration should be, who is the customer for the analyzer data? We forget who the customer actually is for analyzer information. We install an analyzer, but if nobody's going to use the data, what's the point? we install an analyzer and the information is not timely enough, what's the point? Our customer is the one who ends up paying for the equipment, the user of the data, the maintainer of the data. And if we forget who the customer is, we will lose our focus. Our customer is the process system, whether that be the process control system, or whether that be the environmental monitoring system, or whether that be the safety system. One of the things I've not mentioned yet is safety. Safe analyzer systems are a given. I'm not going to preach about how we can design safe analyzer systems and how we must always keep safety in mind. That's a given. So whenever we see any statement, safety's in there, even if I'm not using the words. Classic pitfall number 2, overloading the technician. The guys who maintain this equipment are the least promoted, the least appreciated, and the least enthusiastic people when it comes to anything outside of their work. They focus, they work on the equipment, and that's why they're analyzer technicians. We overload them. We buy new equipment, we don't train them. We order more equipment, but we don't have more people. Our technicians who maintain the equipment are overloaded, but we insist that they do more with less facilities. Classic pitfall number 3, response times. I mentioned response times in the overview. We're pushing for unrealistic response times sometimes. Unrealistic response times, data sheet says, oh, 60-second response time. Do we really need a 60-second response time? Or do we just want it because it says it on a piece of paper? Classic pitfalls. Freezing up a regulator. Oh, you go out on site, there's a regulator, it's got ice on it, and it's the middle of summer, or you're in a humid area, or it's frozen up in Saudi Arabia in the desert. Freezing up a regulator is for a specific reason. It's because the system's not been designed correctly. Too long sample lines. Oh, I worked on one project where we had 600 feet sample lines, 1,200 feet sample lines, 300 meters. Absolute impossibility in terms of response times. And the argument for putting long sample lines in was, oh, we can get away with one less analyzer house. At the end of the day, it ended up costing much more money by redesigning after startup. Changing phases. We've had samples that we evaporate or boil off and then measure. We have samples with condensation. We have samples which actually stick to the sides of the tube and we lose the component that we're measuring. Our diffusion or absorption line there. We all know about moisture and stainless steel tubing, but we also need to think about atmospheric oxygen coming into the sample lines by diffusion, because it can get through compression fittings when you're trying to measure parts per million or even less. It's a classic pitfall in parts per million systems. And a big one, sample pumps. I hate sample pumps. It's a necessary evil sometimes, but sample pumps break down. Single point failure means the whole of the analyzer loop loses its reputation because of a sample pump. So if we can avoid sample pumps, I'm all for it. So, basic design strategies. What should we be looking at? Where should we focus? So, basic design strategy, we should start off with what the analyzer needs versus what comes out the process. It's a basic statement. If the analyzer needs a vapor sample, there's no point in sticking liquid in it and expecting the system to work. It's fundamental, but the number of times we see the wrong preparation of a sample for what is being done to it. So this basic strategy is look at what the analyzer needs, look at what comes out the process. The bit in between is going to be your sample system. If you make it complicated, it'll break down and it'll need lots of maintenance. If you make it too simple, it may not do what it needs to do. The second most important thing in a basic design strategy is understanding the pressure drops that happen throughout the system. A lot of people are not familiar with what goes on inside a sample system. They want the sample system to do a job, but when we're talking about designing a sample system, we have to understand where the pressure drops are and what we have to do to keep the system working at its best efficiency. And that leads on to maintaining the system. Our basic design strategies should include pulling the thing apart, cleaning filters, changing bits and pieces. If we don't think about it during the design, then the technicians who have to maintain it are just going to look at the equipment and swear and curse and complain about another pile of rubbish come out of supplier A or supplier B, and why doesn't anyone listen to them? So what we'd like to do is try and work towards better sample systems, accepting that we will still need sample systems. So where should we focus? Looking at our sample system designs, we've got some key areas and basic strategies, and we've got a whole list of learnings that we've done on other projects. We should not be repeating previous mistakes. So where should we focus? Well, we talked about understanding the pressure drops. Our basic design strategy says we need to understand how a sample gets from the process into the analyzer and how long it takes to do that. In doing so, we need to understand the pressure profile within that system and the stability of the pressure. We'll go through some examples in a minute where technicians who work out on site know it only too well. You turn the flow control on one part of the system and it affects somewhere else because the pressure stability in the original design is not adequate for what we're doing with it. So the flow control within that system is subject to pressure stability, but even simpler than that, the selection of flow control is a bit like when you open the tap to run a bath and you get a tiny change in the hot water, makes it go from acceptable to boiling and burning itself. A little gentle touch on the flow meter and the thing goes off scale. We need to understand the flow control mechanism and focus on it so that the system we get is maintainable and stable. And as a last item on focusing, we need to understand material compatibility. And I don't just mean stainless steel or more exotic alloys, non-L, Hastelloy. I worked on a project recently where we had to use titanium sample transport tubing because the sample had a pH of -2. And when I got a data sheet with pH -2, I sent it back and said, there's probably a typo error here. Somebody's writing pH -2. And they said, no, -2. I didn't think you could have things that were that acid, but when you look at the fundamental definition of pH, it's quite possible to have a super, super strong acid with that amount of hydrogen ions in it. pH -2. Material compatibility for things like that stretches not only from the metal, but into the O-rings, and not just do we use nitrile or Viton or do we use PTFE. There are many choices these days for elastomer selection. And if we make the wrong selection, then the system breaks down. So we need to focus on these things at the design stage and not just put the standard Swagelok 43 series ball valve with Viton O-rings in it, so that when we put hot benzene through it, the O-rings swell up and the ball valve blocks. So, understanding the pressure drops. Let's look at a basic system. You can't get more basic than this. I looked up flow rate calculations on Google, and the simplest I could come up with is you have a restriction device of some design, you have a pressure on one side, a pressure on the other, and if P1 in this example is greater than P2, you get flow Q in the direction of the arrow. That's not rocket science, it's basic fundamental flow, but it highlights the fact that we need a pressure differential for flow to take place. If the differential's too small, the flow's too small. If the differential's too big, it means what goes on downstream is possibly outside the design of what we want it to be. So in the real world, pressure drops aren't as simple as that. Here's a pressure loop. Can you all see my cursor pointing at this item? Can you help there? Any feedback? No? Don't know. Okay.
Sorry about that, Trevor. Hey, had to mute myself. Did you click the things up in the upper left-hand corner, your pointer?
That's it. That's what I had to do. Pointer. Right. Yeah. Bear with me. What's the pointer look like? How about that? No?
There you go. Yep, we see the yellow. You just circled something in yellow.
Yeah, okay. Now, can you see I've got a big arrow pointing at this area?
We don't see the arrow thing.
So if I do that, can you see it?
It shows now. The arrow showed up. Yep.
Okay. And how do I clear that?
You might have to click next slide. Sorry about that.
Okay. We've got a process takeoff here, starting with a high pressure. We may have to drop the pressure with a regulator at the takeoff. Our sample is going to travel a distance, and in traveling that distance, it will need energy to do it, energy in the form of a pressure drop. We get to our sample system at this pressure, and contrary to normal ways, we now work back from the return. We have to get back into the process. This particular process is going to flare 0.2 bar, marginally above atmospheric pressure. It's going to flare header locally, not very far. So we end up with a pressure difference in our system, which goes from the inlet of the system to the outlet system. This is our pressure drop. This is the real one. This is how analyzer systems work. We tend to use that pressure drop to control a flow going through a needle valve and a flow meter. And likewise, we will use that pressure to go through the analyzer itself, in this case going to spent sample return of some description. But we have a pressure drop profile that starts at this end and goes all the way through to the analyzer and back to process return. So we're still using the P1, P2 flow, but it's a lot more complicated. In terms of pressure stability, what does that particular system give us? We said we put a regulator in here, so that should fix everything, shouldn't it? We stuck a pressure regulator in, pressure is controlled by a device. But if we go through and we look at what really happens in this system, let's push things to the limit. Let's assume we have a 30-second response time requirement out of this system. It's hypothetical, But this is the kind of thing that goes on. We set our regulator at the takeoff to a certain pressure, but we ram so much flow down this particular tube to get to the analyzer that we lose a lot of pressure in the supply line. The figure we've got here is we're losing 30 to 40 psi 2.3 bar in the supply tube, and we end up with a workable pressure here. It's not a problem. Everything's perfectly fine until we start changing flow rates. With a flow rate of 29, my eyesight's getting terrible, too many computers, 29 litres a minute, a 30-second response time. If somebody comes and fiddles with this fast loop flow meter, the flow control says that everything changes within the system. If we just change that to 26 litres a minute from 29, that's not very much. We tweak it, the response time's only changed a couple of seconds, but the pressure's gone up here. We've got a change in pressure even though the regulator at the takeoff is unchanged. We've got a dynamic pressure balance within the system, and all that's going to happen here is this flow rate going to the analyzer, the flow meter will go up when we change this flow meter, and that is so annoying on site. Trying to balance a system that is designed like this means you spend half your time setting something and resetting something that you don't need to do. So pressure stability and flow control should be where we are focusing. We talked about flow control and how we actually work a system. I can't zoom in. Yes, I can. Has that zoomed in for you guys? Yeah, probably. So I've got a calculation here of CV, flow coefficient. Most of the time, analyzer people don't calculate flow coefficients. Process people do. They know and understand the flow coefficients of control valves, of relief valves, of pipes, of vessels. But when it comes to analyzers, we talk about such small CVs that people don't bother. This is 0.0449 in terms of a number. It doesn't mean much to some people, but if you look at, this is the fast loop, look at the flow control coefficient of the needle valve that we would need going to the analyzer, 0.0006. It sounds very small, and it is very small. The needle valve that we need to control properly is a very small one, and the flow meter manufacturers don't fit those. They provide you with a tap on the end of it. They charge you a lot of extra money to stick a needle valve on a flow meter, and in reality, they just provide you with a tap. There was one analyzer manufacturer, one flow meter manufacturer who used to make a soft seat needle valve for their flow meter, and we found out that it was actually, the soft seat was made out of lead. And one of the advantages of lead is it's really soft and it deforms quite nicely when subject to load. So we found if we screwed the needle valve in really hard, way past the point that you should do, the lead formed the shape of the needle valve, so that it then started to perform as a proper needle valve instead of an on-off tap. They stopped making that model, unfortunately, and we could no longer buy that one. We should spend more time looking at flow control, because at the end of the day, it makes for a better system, a more stable system, and one that gets a better reputation because we don't work on it as much. Material compatibility. Our focus for material compatibility should be on our metals and our elastomers. We all know stainless steel is better than carbon steel. We all know that Teflon, PTFE, whatever variant, is more resistant but not as pressure containing. But we don't think about elastomers. We think we know that PTFE is better than Viton is better than nitrile. But when it comes down to it, if we're going to design a sample system, if we're going to improve the reliability and maintainability of sample systems, we need to be better than thinking that we know it. We need to become more expert in materials. The number of times we talk to suppliers like Swagelok, and they say, oh, we only make this particular variant. And we have to say, but as a customer, we want something different. We want something better because our particular application does not fall into your one part number fits all categorization of your catalog. So our material compatibility needs chemistry experts, it needs metallurgists, it needs people with experience and knowledge, and also people who are prepared to stick their necks out and say, I know that the best possible thing for this application is ABC. Far too many examples of people not committing to making a decision, and you end up with a system by default rather than a system by design. So, moving on to understanding response times. Let's talk about what is the analyzer response time, what is the sample system response time, and when it comes down to it, we need to agree a response time for the system. It's easy enough to say that the response time of our oxygen analyzer is a T60 response time in 120 seconds. At the end of the day, that's useless to anyone except the salesman who can quote you numbers, and we meet a hypothetical specification. T60 figures are useless, T90 are not much better. We need the time taken for the analyzer to respond to a change in what's going into it. And if that takes 5 seconds, then at least we can quantify it. If it takes 5 minutes, it doesn't matter as long as we know about it and the application can handle it. We use cyclic analyzers an awful lot. We still use automated laboratory techniques in automated titration and devices such as TOC analyzers. They have a finite response time. They take 8 minutes, shall we say, to produce a result. So their minimum response time is 8 minutes. And it's no good process saying, oh, we need a 60-second response time out of the TOC analyzer. If it's got an 8-minute cycle time, it's never going to be 60 seconds. The sample response time is part of the overall loop response. And the number of times we see written in a specification, 60-second response time. Why is it 60 seconds? Nobody actually knows. It's been written in specifications since 1959 when that document came out. Somebody once said, oh, we've got to have a response within 1 minute. Let's agree a response time for the system, and if we can't meet that response time, let's calculate what we can actually achieve, and then let's optimize that response time and then discuss, is it acceptable? Rather than just throwing this 60-second figure in, we need to know what is needed and is it achievable, and to achieve it, is it safe and realistic? And having gone through all of that, then, is it maintainable to actually do all of that? So having agreed it, let's see some pictures as to see what's needed. The time base of this graph is completely made up. It's done purely to illustrate an example. I'm showing here as an analyzer, cyclic analyzer, 90 minutes, could be 90 seconds, doesn't really matter. But we can see that the analyzer is showing a change in process. Every time it produces a result, we're seeing a difference in the process. And we can extrapolate, postulate, hypothesize, trend, whatever term you want to use. We can guess that the process is responding in this type of cyclic up and down change. That's on a 90-minute cycle time. If we were to increase the frequency of that just to 60 minutes, we get a completely different picture. Oh, 60 minutes, look. All we've done is take more data, and our picture has changed from a simple sinusoidal curve to something else is going on completely unexpected. So we're not seeing what is going on in the process. Our response time is inadequate, but we're starting in the worst possible case and working backwards this time. If we reduce that response time to 30 minutes, our picture changes again. I'm coming to the point where we can see what is happening by making the analysis faster. Look, if we go to 10 minutes, the picture is completely different. We started off with a 2-peak sinusoidal curve, and this is maybe what's going on in the process. Agreeing what's needed is one of the starting points to enable us to design the system. And if the process responds so fast that we need fast results, then that's fantastic. We've got a starting point, we can try and design it. But if the process takes 12 hours to respond to a change in concentration feeding the reactor, then we don't need a 60-second analysis. It's a kind of accepted norm that your measurement has got to respond at least twice as fast as the process. Otherwise, you can't see what's going on. So, general rule, somebody tells you 60 seconds, well, the process has got to be changing within a couple of minutes. And if it's slower than that, then the 60-second rule shouldn't really apply. Having established our response time, we need ways of calculating it. And I looked up, there are 7 different ways that I can calculate the pressure loss in a flowing tube or pipe. It's no wonder we all come up with different answers. I'll tell you the pressure drop is 15 psi. Somebody tells me, no, it's not, 17. And they're using an equation that they believe to be accurate. In all honesty, we don't calculate pressure loss, we estimate pressure loss. What we should be doing is designing for an estimate, and then when it comes out on site and we've actually got some feedback and we know what the pressure drop is and we set the regulators and flow meters to our optimum conditions, we should then be writing down those optimum conditions. But how many times do we have to build a system where we have to put the set point of the pressure regulator on an engraved label, and when we get to site, the engraving's wrong, we have to change it. So loads of different ways of calculating them. I've got laminar flow, small pressure drop, medium pressure drop, high pressure drop, and I've got some gorgeous equations. The Weymouth equation of pressure drop, invented in 1912 and still used. Panhandle A and then Panhandle B, gorgeous names for equations. They're used for compressible gases along long lengths of pipe, and they come up with a different answer that's maybe more accurate. So we calculate pressure drops through the system using different tools. For analyzer sample systems, the tools that are available are pretty inadequate. Basic process pressure drop calculations don't show us what's going on. So we've developed our own spreadsheet which allows us to look at what goes on in the sample system, and we can estimate sample system pressure losses, so we know what's going on in the system. We know what to expect for our response times. And having established where the pressure drops are in the system, we can draw a simple picture to show us where the sample is spending most of its time. I'm a great believer in pictures. It's a lot easier to show what's going on than to explain it. Many, many years ago, somebody commented to me, if you need to explain a picture, you've not drawn it properly. This particular picture, if you could read it, and that's where I've not drawn it properly, the font's not big enough. This shows the pressure drop in the sample probe, the pressure drop at the front end of the regulator at the takeoff and at the back end of the regulator, the sample transport line, and then the sample system to the analyzer. We don't often calculate that, or we don't calculate it accurately. If we want to optimize response time, if you draw this picture, it's real easy to see where we should be working. We should be working at reducing the response time to the analyzer, not making the fast loop run faster, but the first thing we need to do to optimize is increase the flow rate going to the analyzer if that's possible. If we do that, the picture changes immediately. So just by increasing the flow to the analyzer, if it can take it, we've changed our focus for response time. Looking at this picture, it's easy to say, even without a label, that this is where we should be looking at next, and this is sample probe, sample takeoff delay. We're really interested in how long it takes to get from the tip of the probe to the analyzer output, whether that be 4 to 20 digital or whatever it is. And if we're spending 50% of the time in the sample probe and then it whips through everything else, then we can focus here. So if we were to change the design of the sample probe in this particular example, our overall picture changes. We can see now it's spending most of its time in the transport tube. You can't do much about that without increasing the flow rate, and if you can't do that, you need to move the analyzer closer to the takeoff. It's all about what do you actually need versus what you want or what you think you want. So moving on to our future trends. We've looked at sample system design, which appears to still be making the same mistakes as we did in 1959. We like to think we're better. We need to learn from what we've done. We need to listen to feedback from installations that we've had, and we need to use this information in our future designs. But what are trends giving us for improving our lot in terms of analyzers? Well, the ultimate that they'll all tell you is, oh, you want an inline analyzer. You can put our analyzer directly in line, don't need a sample system. I think that's fantastic. It works for some equipment, but does not work for others. A typical inline analyzer might be an Oxton analyzer, it might be a TDL, it might be a fiber optic insertion probe, it might be an online refractometer or an inline refractometer. They have minimum response times, but if they break down, you've got the problem of taking them out of the process. So I see more developments coming in inline analyzers. We're working more with fiber optics. Fiber optics allow us to use spectroscopy techniques to get composition information, and that allows us to mount the equipment either next to the process takeoff or in a environmentally controlled analyzer shelter, and use fiber optics to carry the information back to us. Developments that we must work on are analyzer data systems. We have all of this information being generated out in the field, and we increase the complexity of the information and we increase the loading on our maintenance crews, but we don't provide them with the tools to analyze the data. The only way that we can plan and control our future is to analyze the past. So data systems really need to be developed much more than they are today. Not only developed, they need to be accepted and implemented, leading to almost self-diagnostic systems. it's a fancy word, but it could be very simple as monitoring the pressure in the carrier gas header on an analyzer house and plotting the decrease in the pressure in the bottle with respect to time, and using Excel to project forward when the bottle's going to need changing. A self-diagnostic system should tell us that it's going to need some work in the next couple of weeks so we can plan it. We're constantly told that planned maintenance is a lot cheaper than reactive maintenance, but it's so difficult to plan when we don't know what's going on. Perhaps then our final future trend is the dreaded NESI. It's a term that we've probably all heard of, but not many people know much about. NESI is expensive and not widely accepted. What is it? It's a sample system initiative. It's miniaturization, but it's not so much have you got the money to implement it, it's can you generate the return. NESI is supposed to increase the reliability of the system through automation. We're supposed to be able to make things smaller. We're supposed to be able to make things cheaper. We haven't got onto the cheap bit, but some of the spin-offs from it are really size. And I made a 32-stream sample system fit in a small box using modular components. So there can be good cases for implementation of high technology, best description, but it doesn't work for everybody. It's not the be-all and end-all. It's not the panacea for sample system problems by any means, but it's a future trend. So what do we look for tomorrow? I think tomorrow our industry is still going to need sample systems. Our industry will still complain about the costs. The EPC will moan about how much the supplier charges, then they mark it up and the end user complains about that. And then the spare parts are expensive. We still will continue to complain about the cost. And I think our industry will still do it wrong. But we need to change that. We need to change it by focusing where we look, where we concentrate, and we need to listen to feedback from others about how to improve. So tomorrow our industry will need more people to understand how to do it before we lose the art. I've been doing this 40 years. The average age of analyzer expertise is constantly increasing and we are losing experts. We need to bring more people into this aspect of industry, and we need to help them understand what we do and how to do it themselves before we lose the art. So at this point, I'd like to hand over to questions. We're bang on target as far as time's concerned. So where are we? Let me hand you back to Josh. Can you come in now, sir?
Yes, sir. Thank you, Trevor. Appreciate your great presentation. And again, we'd love to get all of your questions. To participate in today's question and answer session, please go ahead and submit those through the chat and the Q&A window. We've got a couple of them coming in here. Let me go ahead and read those off to you. First one, a turbidity instrument is subject to bubbles forming and adhering to the silicon sealer at the bottom. Once the bubble grows large enough, it releases and spikes the instrument. How can I remove the gases in the water that allow this to happen?
Oh, cool. Difficult question, like it. There are two reasons gases will come out as described. It's either because the pressure's dropped and the gases were dissolved, a bit like opening the top off a bottle of Coke. They come out of solution and start collecting, or they're free and hanging around in the first place. If we're taking a sample and it's got bubbles in it, then we need to get rid of the bubbles in some kind of overflow chamber, and that's probably the simplest way to make sure that you don't get the bubbles coming through. but most of the time the bubbles that I see on the turbidity analyzer is because of the pressure drops in the system. Upstream from the analyzer, we stick a needle valve and a flow meter, the pressure drops going through that, and the bubbles start forming sometimes even in the flow meter. For a turbidity analyzer, I always stick the needle valve and flow meter after the turbidity analyzer and run the thing under pressure as much as the sensor itself will take to stop the bubbles coming out. So those are the two areas that I'd look for on that, sir. Next one.
All right, thank you. All right, we've got another question. It says, are there any good resources on sample handling system design in the form of a textbook?
There's two textbooks that have sort of become the gospel according to. Many years ago, there was, many years ago, Ken Clevitt wrote a book on analyzed sample systems. It's become the de facto must read. If you send in an email on that subject, I'll dig out the title and the ISBN number. But I think last year or the year before, Tony Waters, who was Mr. Measurementation, Mr. Yokogawa, Tony's kind of updated that book and written his own book on sample handling design. And that I can highly recommend. So Tony Waters, Sample Handling Systems, again, the title, I don't know what by heart, but that's pretty good. There are some, are they ISA standards or are they UL standards, or I'm trying to think of the correct terminology, but there are some industry standards that have been written that try and address basic sample probe, basic sample system, sample point selection. And so those exist in reprints for the Institute of Petroleum and things like that. So yes, there are some. Josh, if you want to send me an email separately on that subject, I'll dig out a list and send it back to you.
Okay, sounds good. And real quick, we do have one of the participants that mentioned Tony Waters' Industrial Sampling Systems is one resource people could use. So
fantastic.
Throw that out there. All right, we've got another question. He says, I would like to know more details about flow meter scale selection. I know the analyzer ideal flow, so that for the flow meter Biosphere analyzer, but how do I choose bypass flow meter scale?
Well, bypass flow meter. You need to calculate your response time. Sorry, estimate. I still use the word calculate. You need to start off by looking at what response time you need from the system. You need to plot your pressure drops through the system and the response time profile that you get, as in those bar graphs I showed up. That gives you a fast loop flow rate. Then you've got your fast loop flow rate, and between the two, the analyzer flow rate and the fast loop flow rate, you can size those flow meters successfully. Sometimes if you stick an analyzer, for example, if response time says you need a total flow rate of 5 liters a minute, and the analyzer itself needs 5 liters a minute, you don't need a fast loop. You don't need a bypass. Maybe when you're working on the equipment, you might want to keep flow going for a different reason, but it's a balance between what the analyzer needs and what the total flow rate requirement is to meet the response time. So a good calculation program should give you those numbers by default. Okay, sir.
All right, thank you. All right, here's another question for you. It says, should a sample pump be required for the process? Would you recommend an electric pump or a, I think it's pneumatic pump?
Yeah, I understand the question. Pneumatic pumps have yet another item to fail. Electricity is straight on off, but introduces the certification requirement for a hazardous area. Pneumatics get around that, but the trouble with a pneumatic pump is that it needs instrument air, it needs oiling, lubrication in certain circumstances, and the flow rate will be dependent upon the pressure regulation of your air supply There's too many variables in a pneumatic pump. There are times when pneumatic pumps are better, and that might be in a submerged situation where you want to drop a pump down into a swimming pool type sampling out on a collection sump or a pit or something, and the type of pump there, you can get the sludge gulper displacement diaphragm pumps that operate a pneumatic flip-flop. They work far better than anything else because that's what they were specifically designed to do. In general, I would prefer electric, but there are always exceptions, so it depends on what you're doing.
All right, thank you. All right, we've got another question that's come in, another couple of them, and I'm actually going to unmute one of our other presenters as well. They asked, is there any toolkit available from Yokogawa or others that work out sample flow rate? So Trevor, maybe if you have some ideas there, and I'm unmuting Scott as well, one of our other local experts, maybe you could help us out with that.
Yep.
Yeah. There's not exactly a toolkit or a tool available for this. This is an engineering service that Yokogawa offers. We can, if you get with one of us, with me, or send your email address in, we'll put you in contact with someone, and we can discuss some services we can provide to help you with this.
So to follow up from that, we've got spreadsheets that we've evolved into ways of estimating sample system design. I use those spreadsheets every single time. The problem of passing that to someone else to use is that you need to understand how it works. There's an element of training associated with it. So it's not just something you buy off the shelf. If you need that kind of calculation ability, then you can get hold of some software, but you also need some pretty good understanding of how it works to be able to use it effectively. Okay?
All right, thanks. All right, here's another question. It's kind of a little bit simple, and we may need some additional clarification, but it says, sample pump position before or after analyzer. I think probably should you have your sample pump position before or after the analyzer, and then for gas and liquid.
Say that again, could you please?
Yeah, it says sample pump position before or after analyzer for gas and liquid.
Yep. I got a very simple understanding of pumping before or after. Pumps are designed to push, not pull. In the simplest form, if you suck a sample, in other words, you put it after the event, you can only suck a full vacuum. So if you start off at 1 atmosphere, the maximum you can possibly suck with an infinite amount of money is -1 atmosphere. That's practically and technically impossible. So it really depends how much money you want to spend, how close to a vacuum you can generate. In terms of pushing a sample, that's what pumps do. You can push tens of bars, 20s of bars. In one particular example, I stood on a compressor platform where the gauge was reading 45, and then underneath it said times 1,000. So 45,000 PSI. So there's no limit to what you can push, but there is a limit to what you can pull. So for me, pumps always go before the analyzer, if possible. There's always reasons why not, maybe. And they should go at the takeoff as soon as possible, and then push the sample through the system. Next.
All right. You feel welcome to continue to submit your questions. Again, if we don't get to your questions, we'll follow up with you after this event. I've got one more good question for you. Why is a probe required versus a simple nozzle or a valve installation?
Oh, I've done this calculation so many times. You talk to the process people and say, okay, you want to take a sample off of this 6-inch pipe. You're going to put a 2-inch valve on it and a 2-inch nozzle. And then you calculate the volume in that middle 2-inch stub, because they've welded a saddle to the side of the process pipe, and they stick a 2-inch nominal bore gate valve on it, and then a flange on the end of it, and take the sample off. Well, if you do that, you've got probably 10 times the volume just in that bit of the rest of the sample system put together. So why do we use a sample probe? First thing is we want to take a sample from the inside of the process. We don't want to take it from the dead end of a T-piece with a valve on the end of it. We want to get a representative sample from inside the process, and we don't want it to take ages for that sample to be refreshed. So the dead volume of a sample probe can be in just a few cc's, whereas the dead volume of a direct process tapping is hundreds of times that, and it affects the response time and the representativity of the sample. So that's why we use a sample probe. There may be reasons why we don't, but that's one good reason why we should. Next.
Okay, perfect. Well, we're just after the top of the hour. We're going to go ahead and close off for now. Again, please go ahead and continue to submit your questions in your chat. We'll go ahead and stop right there, though, but we'll make sure to follow up with you with any additional questions that you might have. Again, if you do have other questions, here, let me grab this back a little bit. You can always contact us. You can contact Dale Cathy, who works a lot with these, or Trevor Hibbage, or Scott Edelman, and any of us will be happy to help you with any of your questions that you might have or needs that you might have. With that, we again thank you for your time. Thank you for joining us. And Trevor, thank you for your presentation.
You're very welcome.
All right. Thank you.
Okay, signing off. Have a wonderful rest of Wednesday, people.